Assalamualaikum warahmatullahi wabarakatuh. Budaya dan pariwisata. So good day everyone. We are very honored to have Professor Andrea Baldi from Vrije Universiteit Amsterdam in Netherlands. He is here with us to share his expertise, insights of plasmonic chemistry. So a little bit history. I was introduced to Professor Baldi to Vrije. Vrije is from Department of Physics in Indonesia. Vrije was his postdoctoral fellowship with Baldi's group at DIVA, that's Institute for Fundamental Energy Research, located in Eindhoven. And back then I was postdoc at Professor Mohammad's group in University of Sweden, who was also former supervisor, and we were collaborating on developing nanoplasmonic sensitive nanoplasmonic hydrogen back then, which fruitfully, and we are very proud that the work is now published this last year. And then Professor Baldi has worked in plasmonic chemistry and been published in many prestigious journals out there. And his experience spans from postdoctoral at Delft University and then Stanford University under supervision of Professor Jennifer. For those of you who are working with plasmonic nanomaterials must have this is one of. And then after that, Professor Baldi was appointed as a group leader of nanomaterials for energy at DIVA. And now he is associate professor at Vrije Universiteit Amsterdam. So I believe this talk will inspire us, will learn from Professor Baldi. So I encourage you to engage and hopefully can participate actively in the discussions. And the last part of this, I am representing and Vrije so from Indonesia and to make this meeting possible. So that's a bit introduction for me.
Thank you very much, Ivan, and thank you for the kind invitation and the hospitality here in BRIN. It's a pleasure to be here. Thank you also, Terry, for making this possible. I'm flabbergasted at how many there are of you. And hopefully by the end of this talk, you will understand what I mean by plasmonic chemistry and how we can activate, actually we can much more with plasmonics. But today I'm going to talk about how we can activate chemical reactions by shining light on tiny. So this is a picture of the Vrije Universiteit. Actually, this is the building where Fanny and I have been suffering for the 2 years together. Soon this building will be dismantled, and you can also see the work in progress of the new building that's built over there. Hopefully, it's going to be looking a little bit better. But if you're ever coming to visit, this is what you can expect to find. And in fact, you're welcome to visit. I'm just discussing potential positions for postdoctoral researchers, PhD researchers, instead in spending some time in Amsterdam in particular to do some work on, for example, nanophotonics and applied nanophotonics. My door is always open. You're very welcome to come. So before I start, I should also acknowledge the people that did most of the work. These are some of the people that I have included in the storyline of today. Definitely not all the people that passed through the group. But the story that I'm going to tell you about is mostly related to the work that was done by, in particular, an amazing PhD student who graduated from my group a few years ago. And also some collaborators at the University of Eindhoven, and of course, the funding organization. So this is actually the photoconversion material section. That's the section that I work with, and I'm sharing this sector with another group leader, Charushita, actually Sven also became a recent PI, we're hiring another PI, so this section is growing, and as a proof that Terry was actually a postdoc in my group, see Terry also here in the picture. This was in July 2000, last year. We should take a look. Now, what do we do, like in our section? Well, in my group, we do a few things. The first thing that we really enjoy to do is to synthesize nanomaterial. And even though I am in a physics department, I was educated as a chemist, so I really enjoy being in the chemistry lab. And we do some work on nanomaterial synthesis, for example, like core shell nanoparticles, so silver nanowires. And then what we do with these nanomaterials, we typically shine light on them. And one objective that we have is to shine light on these cuvettes containing suspensions of nanoparticles to drive chemical reactions. And today I'm going to talk about how we can grow stuff around these nanoparticles by shining light on them. But we can also use light to sense processes that are happening at the surface. For example, gases being absorbed, and that's part of the work that together with we did, and together in collaboration with the University of Chalmers in Sweden. But we are also developing new tools to use, for example, spectroscopy to measure temperature at the surface of these nanoparticles by using some temperature-sensitive Raman probes. And also we use light effects in not only in suspensions or individual nanoparticles, but also in regular periodic basis nanoparticles. So, of course, I don't have the time to touch upon everything here today. And so disappointingly, I'm only going to show work that is related to this plot. But before I go into the story of this work, I want to give a little bit of an introduction to what is plasmonics, and why and how does it, what are the advantages that we can get out of it. So maybe as a motivation slide, why should we be interested? I'm going to quote this paper that came out a few years ago in Science, and it's called Applying Plasmonics to a Sustainable Future. And the paper starts by saying that chemistry is fundamental for powering our society, and that is certainly a fact. And plasmonics offers the ultimate spatial and temporal control over light and photochemistry. And so, hopefully, by the end of today's talk, you will see what this sentence means, and you can understand the power of plasmonics in order to really drive chemical reactions and light-activated chemical reactions with extreme spatial and temporal control. Okay, so this is the title of the talk. Plasmonic chemistry, activating reactions with metal nanoparticles. The outline is going to be, first of all, I will explain what we mean with plasmonic, and several meanings. We talk about plasmonic in metal nanoparticles. We don't talk about, for instance, surface plasma polaritons, probing plasmas at the metal semiconductor interface. We're really talking about localized plasmas on individual nano-objects. And the second part, I'm going to talk about how plasmonic chemistry can work, what are the fundamental physical mechanisms that can be exploited to do activate chemistry, and what is kind of the physics behind some of these processes. In particular, I'm going to focus about the effect on temperature, because temperature is a very highly debated aspect of these plasma-activated chemistry reactions. And then I'm going to tell you the story of how we started to work on this plasma-activated chemistry and what kind of steps we took on the way. How many hypotheses we tried to confirm and actually didn't match, and what we learned in the process. Okay, so what do we mean by plasmonic? And by all means, if you have questions during the presentation, please raise your hand. I love questions, so don't be afraid to move on. Okay, with plasmonics, we intend the fact that if you take a metal nanoparticle and you shine light on it, this metal nanoparticle can both scatter light in all directions, but it can also absorb. I've indicated this two different types of arrows. There's no physical meaning to the shape. The reason why they can do it is because these are metals, so they have a lot of free electrons, and these free electrons can oscillate at the frequency of the electric field that is incoming. And so, if they oscillate in phase, then they can have essentially a strong response to the electromagnetic field, and leads to scattering and absorption. The way we conceptualize this, actually, if you want to fully solve the problem of, the Maxwell equation problem of a plane wave on a spherical object, you have to kind of express a plane wave in spherical coordinates. It's mathematically kind of complex. So the authors of the book that you use to study it. They write, the reader who has painstakingly followed the derivation required virtue through suffering. I cannot give you either virtue nor suffering because we don't have time to go through the whole range. But I'll get an approximation that works for very tiny particles. And so in first approximation, you should get a sense of where these plasmon mechanisms are coming from. So how do we conceptualize them? Well, we use the concept called cross-section. And in fact, we use two concepts called scattering cross-sections and absorption cross-section, and the sum of the two, extinction cross-section. Now, these are cross-sections, meaning that they have the size of an area. So if you want, you can think of it, of the extinction cross-section as the size of the shadow that one of these nanoparticles will cast on the screen behind it. Right? The bigger the shadow, the bigger the extinction cross-section, the bigger the amount, the larger the amount of scattering and absorption. Now, you can see that both scattering and absorption are proportional to a quantity that is called alpha, which is called the polarizability. Alpha is a measurement of the polarizability, is a measurement of how much an object can be polarized by the electromagnetic field. And this polarizability depends on the permittivity of the materials that are constituting the object. So if you take a sphere of, let's say, gold in vacuum, the polarizability of this gold sphere in vacuum will be dependent on the permittivity of gold and vacuum. And these are, the permittivity is just a characteristic of a material, not of an object, right? And where the permittivity is a measurement of how easy it is to polarize. So the larger the permittivity, the larger the polarization vector in a certain element. If something gets very polarized, then the permittivity will be high. Now, there is an easy way in which we can calculate. So if you want to calculate the polarizability of a spherical object, as I said, you have to go through virtue and suffering. But there is an easy approximation if we have particles that are very small. And so in particular, the limit or the condition that you can apply is that if the radius of the particle is much, much smaller than the wavelength of the light that is incoming. So in a way, the opposite ratio of this scheme here. So here the wavelength is short and the particle is kind of big. Now think that the electromagnetic wave is much bigger. And so this is a condition that, for example, applies to any nanomaterial within a few nanometers or a few tens of nanometers. And if you irradiate visible light that has a wavelength between 400 and 10, right? In those cases, the nanomaterial would be much smaller. Now, in this approximation, which we call the dipole approximation, the particle is so small that it behaves like a dipole. So it's essentially responding to the electric field like a dipole. And we can write a polarizability with a simple equation that is 3 times the volume of the particle times the permittivity of the metal, epsilon, minus the permittivity of the surrounding medium, epsilon L. And this is divided by epsilon plus 2 epsilon. Now, the beauty of this equation is that if you look carefully, you expect a resonance at the so-called Frolic condition, where the permittivity of the metal is minus 2 times the permittivity of the metal. So when that happens, the denominator becomes 0 or close to 0. The polarizability diverges, becomes very large. And if the polarizability is divergent, then the scattering cross-section, the closure cross-section, will see. And so in conditions where the permittivity of the metal is minus 2 times the permittivity of the surrounding, then you expect to have a very large polarizability. Now, let's have a look at one example. And a typical plasmonic metal that we use is silver. So I'm going to plot the permittivity of silver. Now, in fact, the permittivity is a little bit of a complicated quantity because it has a real component, imaginary component. The imaginary component tells us something about the losses in the material. So how much the electromagnetic energy is losing its amplitude essentially by propagating the material. But if we plot it in the UV to visible range between 300 and 500 nanometers, the losses in silver are essentially 0. So we can neglect the imaginary component. And so the permittivity will just be the real part of the permittivity. And now let's suppose that we have a silver nanoparticle, and let's say that we are in vacuum. So the permittivity of vacuum, the relative permittivity of vacuum, of course, is 1 because it's time with respect to vacuum. At which wavelength do you expect to have a plasma resonance for such a silver nanoparticle in vacuum? Anybody? Ask questions so I can trade. Oh, yeah. Yes. So this goes from -10 to +4. I apologize if the labels are too small in the back. 400 in the vicinity, right? Because we want the Froley condition to be satisfied. Right? We want the permittivity to be -2 times epsilon n. Epsilon n is 1. So we want the permittivity to be -2. And so if we look at it, it's -2 around here, so maybe between 350. It's actually closer to 350. In fact, if you put -2, you expect that within this very simple dipole approximation, you would expect the resonance of 350. Now, if you solve Maxwell's equation, you do the full treatment for a silver nanoparticle vacuum. This is the extinction cross-section area. A resonance exactly at 350. So this condition for a good metal that is non-lossy, then really applies. It really teaches us what is a plasma resonance. So plasma resonance is a spike in the amount of light that is scattered and absorbed, so a spike in the extinction at a wavelength where the Froley condition is happening. And that's the reason why we use metals, because metals are the only materials that have negative permittivity, right? Otherwise, this Froley condition will never happen because the permittivity of the surrounding medium always be positive, so epsilon has to be negative. That's why plasmonics is in metals, because we need that technical. So I have to add a caveat. Like this is a plasmon resonance for a very small spherical particle of a good conductor P5. And so there is 4 caveats. And this all of these 4 are really important. If you think about it, this was for a very small particle because the particle has to be the radius that is much smaller than the wave. It is also of a spherical particle. This is in the small particle approximation. It only works with spherical particles. Of a good conductor because we neglected any losses, epsilon to the imaginary component of the permittivity, we set that 0. And also it's in vacuum because we have assumed that the permittivity of the medium is 1. Now the truth is that all of these things actually affect the plasmon resonance. So if we don't have a very small particle, start to increase the size of the particle, the plasmon resonance will shift towards longer and longer wavelengths. And similarly, if we don't have a spherical particle, say we have an elongated particle, also the plasmon resonance starts to evolve, have multiple peaks, and maybe shift to longer wavelengths as the non-spherical particle gets bigger. Again, if it's not a good conductor, if we go from silver to, for example, gold, the Froley condition will happen at a different wavelength, and therefore the plasma resonance will be with a different color. And finally, in vacuum, so if we go from vacuum to air, for example, to water, we can see a net shift of the plasma resonance because the dielectric environment of our nanoparticle is changing. And so we can use all of these characteristics to both tune the color of at which we want the resonance to happen, but also to follow what is happening on the surface of the nanoparticles. And in fact, I will show you some examples in which we measure the plasma resonance of a suspension of nanoparticles. And by looking at tiny changes in plasma resonance, we can deduce something about what's happening on the surface. Okay, that is my short, one-on-one introduction to plasmonics that we use. Now, how does it work? Why are we interested for chemistry? Well, there are a couple of things that are very important and very interesting to us. The first one is that metal nanoparticles can actually focus light into sub-wavelength region at the surface. Now, what I'm plotting there is the same silver nanoparticle that we calculated before. This is a 10 nanometer silver particle, but we saw that it has this plasma resonance at 350 nanometers, right? It scatters and absorbs a lot of light. And now I'm also plotting here in the blue shaded areas the electric field intensity E squared enhancement divided by E0 squared. So this is the electric field intensity divided by the electric field, the intensity of the electric field incoming. So it's essentially how much the electric field intensity is amplified at the surface of this particle. Now, if you look at it, if this is a 10 nanometer particle, the electric field intensity is only amplified within the first maybe 1 or 2 nanometers. But this electric field has a frequency or a wavelength that corresponds to 350 nanometers, right? So if you put it in scale, this is a wave. Now, this metal nanoparticle therefore has this capacity of compressing electron energy, essentially in very tiny volumes at their surface. And so we can use this. For example, any photocatalytic process will depend on the electric field intensity through the Fermi Goldman. So if you have a very strong field intensity on the surface, then you can amplify or accelerate further processes. Of course, we use this for surface analysis. I'm not scattering the spectroscopy where actually the signal scales with the electric field intensity squared. So we have e to the 4, so even more sensitive. In our research, we use it a lot for gas sensing. That's the kind of research that we put together, even to detect hydrogen. And many more. This is one of the reasons why we like plasmonic nanoparticles for chemistry. There is another reason, and that is, so this is related to what happens to the fields that are essentially outside of the particle. So if you want the fields that are scattered, but what happens to that amount of electromagnetic energy that is absorbed by the particle? Where is that energy going? Well, and the answer to that depends really on the time scales that you're looking at. So at very short time scales, between 1 and 100 femtosecond, this electromagnetic energy can essentially be absorbed like it would in a semiconductor. So by exciting an electron from a lower energy level to a higher energy. So generating pulse in the lower energy level and electrons in the higher energy level. I'm not saying holes in the valence band and electrons in the conduction band because this is a metal. So there is no band gap here. And so the problem with the fact that there is no band gap is that there is electronic levels of stability throughout, which means that this excitation is going to relax extremely quickly, right? These electrons and holes can climb up and down, down and up, respectively. These electronic levels extremely quickly can be combined. And that's why this excitation only lasts for a few femtoseconds. Now, what happens when they recombine? They scatter off phonons and defects and surfaces and off each other. And so eventually they will transfer this energy, this absorbed energy, into heat in the nanoparticle and eventually into heat into the environment. That's a process that typically takes something nanoseconds to heat up the environment. So in fact, the main thing that happens when you shine light on a metal nanoparticle is that they get holes. And so this is something that, well, all these processes can be applied, right? If you're quick enough, you can harvest these hot electrons and hot holes and maybe do some photocatalysis, like redox catalysis. So the electrons will reduce species at the surface, the holes will oxidize species at the surface. Also, you can use it to synthesize nanomaterials. If you have, for example, hole or electron-driven chemistry at the surface of the nanoparticle that maybe this can be activated, but also the heating will affect chemistry. Because chemistry is exponentially dependent on temperature, right? Typically, activation energies follow the dynamics law. So if you increase temperature, the rate of chemical reaction will increase. In fact, for most chemical reactions, the activation energy is of the order between 50 and 100 kilojoules per mole, which means you increase the temperature by 10 degrees, you double the rate. And so even small changes in temperature, like 10 degrees, a huge enhancement in the rate. So temperature is always a big question in these experiments. How often are we making these nanoparticles? Because they are being really efficient here, like they're really efficient at converting electromagnetic energy to heat. And so the only other background that I want to give to the physics background is how hot can we make them? So how hot can nanoparticles get under light irradiation? And this is something that I have struggled for. I'm ashamed to say, but for many years, like I didn't have the right picture of what was going on. And in hindsight, after having learned through the process of maybe every process stages you see, it's actually not very complicated what's happening. It's pure thermodynamics. But I want to show you what is the physics behind it. Okay, let's consider that we have one nanoparticle and we are shining light on it. Now, and we want to know how hot we are making it. So we want to know what is it, delta T of this nanoparticle with respect to the environment. So how hot it is. Now, there are two processes that we need to take into account. The first process is the fact that we are heating up, right? And so we are generating heat by the fact that the particle is absorbing light. Now, that's an easy way to call it the heat generation rate. So this is going to be joules per second. So if you want with power, right, it's in watts. It's simply going to be the absorption cross-section, this is telling us how efficiently the particle is absorbing light, and it's a unit of area. So if we multiply by the power density in watt per unit area, then we get just watts, right? Which is joule per second amount of heat. Great. But this is the amount of heat that we generate every second. However, the nanoparticle is not isolated, perfectly thermally isolated, right? So it's also taking this heat and releasing it into the environment. And so we need to model that as well. That is the heat loss or heat dissipation rate. Now, this is just following a past equation, and the heat dissipation rate is going to be dependent on the thermal conductivity of the surrounding medium. Makes sense. If the surrounding medium conducts heat very efficiently, the heat loss will be faster. It also depends on the particle surface area. That also makes sense. Something that has a large area has more opportunity to lose heat. Something that has a small area has lower opportunity. And it also depends on the temperature gradient across the surface. Now, this is typical, right? If the particle is much hotter than the environment, the heat loss will be fast. If the particle is only a little hotter than the environment, the heat loss will be less fast. And in general, when you have a steep gradient, you have fast or a strong flow. Like a steep gradient in intensive quantity is a strong flow of an extensive quantity. A steep gradient in temperature is a strong flow of heat. A steep gradient in pressure will be a strong flow of mass. Okay, so we have these two contributions. We have the particle that is getting hot and the particle that is cooling down by losing heat into the environment. And of course, we want to know what is the temperature of the particle. So what is the steady state gradient that we can generate? So when are these two heat flow? So if we apply a certain power density, of course the particle is going to get hot, but it's at a certain point within a few nanoseconds. In fact, these two power heat generation and heat loss will be equilibrated. And so what is delta T then? Well, we need to equate these two in steady state condition. And if you do that, you solve this kind of equation. It's exactly the same physical problem of calculating the voltage of a charged sphere. You have to integrate essentially from R to infinity to get the same solution. So for a spherical particle of radius r in a medium of thermal conductivity kappa, the steady state temperature increases given, which is delta T, which is the temperature of at a certain distance from the surface of the nanoparticle. So this is for r larger or equal minus the temperature far away in the end. This is going to be the power generation rate, absorption cross section times the power density, divided by 4 pi kappa r. And if you think about the voltage and electric potential of a charged sphere, it's the same equation, right? It's the electrical density, electrical charge divided by 4 pi epsilon r. How does it look like? Well, if we plot it, it will look something like this. So I'm plotting here the distance, and here the temperature increase with respect to the environment. So this will be delta T, and delta T, it has a certain value inside the nanoparticle. And then outside the nanoparticle, it goes down as 1 over r. So this distance is here at the denominator. The reason why it's flat inside the metal is because the metal is a much better heat conductor than typically other materials that are outside, and so the temperature inside the metal is very much faster. Okay. Now, this is how hot we can make it. But in practice, in our experiments, in our laboratories, we shine a laser on a particle or many particles. How? So, in order to give you a sense of an order of magnitude, I'm going to take this beautifully analytically exact equation, and I'm going to butcher it like ruthlessly. And the first thing that we can do is to say, okay, we don't know what is the absorption cross-section of a nanoparticle. But let's assume that is more or less the area of the nanoparticle, or the projected area of the nanoparticle. This is true for a three-dimensional object. If you take a tennis ball, you shine light on it, the size of the shadow that we cast on the screen behind it is exactly pi plus. For plasmonic nanoparticles, actually, we can make that absorption cross-section larger than the projected area. But in terms of order of magnitude, we're more or less there. Okay? So now we can simplify pi and r. We get Ri divided by 4 pi. Now, typically we run our experiments in water. And in water, the thermal conductivity of water is 0.6 watts per Kelvin. Again, if I remember correctly, the unit, but essentially this kappa is 0.6. So 4 times 0.6 order of magnitude, that's 1. Of course, it's not 1, it's like 2.4, but order of magnitude. So the order of magnitude, the delta T that we can generate is about the radius of the particle times the power density, watt per unit, watt per square meter. Okay, so how much is this? Now, let's consider a 10 nanometer radius particle. So this particle has a 10 nanometer radius, and we put 100 milliwatt of laser. And I'm saying 100 milliwatt only because in our lab we have laser of 100 milliwatt. So that's typical. This is a CW laser, so no pulse. This is constant power coming out. And let's say that we want to have an ensemble experiment. So essentially, we're not focused. That's what I mean. So we have one nanoparticle on the substrate, and we shine from our 100 milliwatt of a laser on top of it, and we don't focus. So it's coming out of the laser, more or less the beam size would be something like a square millimeter, right? If it's a square millimeter, then the power density would be 100 milliwatt divided by a square millimeter. If you convert this into watt and this into meters, you're going to have 10 to the 5 watt per square meter. Good. What does it mean? Well, if the radius of the particle is 10 nanometer, this is 10 to the minus 8, and the power density is 10 to the 5, then we get the delta T is going to be 10 to the minus 3. So if I take a laser out of the box, 100 milliwatt, and shine it on a single nanoparticle, I can really capture that. That's not much, right? We cannot do a lot of chemistry with millicalories, right? Because this is not, you know, we're not, this is the temperature increase with respect to the particle. So this is not getting good. But we can do better. In fact, we can do better in two ways. We can either focus the laser, or we can put more particles next to it. And I'll show you how both lead to higher temperatures. Well, let's first focus the laser. Now, we do single particle experiment. So maybe we put our 10 nanometer particle and now we focus the laser, which is diffraction to be focus. We use a very good lens, very good objective. Get close to the diffraction limit. Order of magnitude is going to be about 1 square micron, right? We can make a spot of 1 square micron. So now the power density is 10 to the 11 because we have gained 6 orders of magnitude in the area. So from 10 to the 5, we go to 10 to the 11 per square meter. And if the radius is still 10 to the minus 8, then we get thousands of gallons, right? So now we can, in fact, ablate this nanoparticle. We just need to focus the laser onto a single one. Way in which we can activate chemistry. And I'll show you again at the top how to use that to grow shells of semiconductors on individual nanoparticles. But we can also heat up without having to focus. And the way we do it, one way, so, well, first of all, we can easily activate chemistry in a single nanoparticle. We can also do it if we use many nanoparticles. Now, this is an example for a two-dimensional, beautifully separated, like square array. This is just to give you kind of a sense of the physical underpinning of this process. And what happens is that if you have a square array of nanoparticles, then each nanoparticle will be heated to this quantity. So each nanoparticle will be hot as it can get through this equation, right? The amount of light that it absorbs minus the amount of heat that is released to the environment. However, now the environment is getting hot because this nanoparticle is surrounded by other tens, hundreds of thousands of particles. And so the delta T local, which is what we calculated before, now has to be modified into a delta T collected, where the modification takes into account the particle radius, but also the size of the illuminated area and the interparticle distance. So the smaller the interparticle distance, of course, the hotter you get. And the larger the size of the illuminated area, so the more particles we are illuminating at the same time, the hotter we get. So we're not focusing, we're just adding particles into. So for example, we saw before that if we don't focus the laser, we have a V spot of 1 square millimeter, and that led to a local temperature increase of milligauss. Now, if you take this equation, let's assume that we have still a radius of 10 nanometers. Now, let's say that we put the particles with a pitch of 50 nanometers. Every 50 nanometer there is a particle. And then let's say that we come up with the same result of 1 millimeter. Now the delta is collected. If you plug in here 10 nanometer, this is 1 millimeter, the square root of 1 millimeter. This is 50 nanometer squared. Now the delta T collected is 10 nanometer. This is 4 orders of magnitude larger than the heating of a single nanoparticle. So essentially, I have my 1 millimeter beam. Before there was 1 nanoparticle, and it was 1 millikelvin hotter than the particle. And now in the same laser beam, I can touch anything optical, but I'm adding particles 50 nanometer away, building a 2 square array. Now there is a lot of particles being there. Now that gets harder, 10 Kelvin. Now, of course, 10 Kelvin is not much, but this is the order of magnitude where stuff is happening. 10 Kelvin means twice as fast in reaction rate, right? And we can easily use 200 milliwatt or 400 milliwatt or 1 watt. So we can go to hundreds, easily, or we can make them closer to each other. So there are a couple of ways in which we can activate chemistry, either using particles or focused particles. And I'll show you how we use both situations. Now, this is the physical underpinning of what are the phenomena that it's understanding of this. So let me get to our journey into driving chemistry. Now, the journey, how it all started for me was when I was a postdoc in California, and I started reading these beautiful papers by different groups, including the group of Chuck Murphy. And what they were showing is that if you have simple nanoparticles in suspension, so they had this solution of silicon. So they were shining a laser onto it, and by tuning the color of the laser, so for example, using 470, 488, 500, and so forth, they could get the color of the solution that was changing. And in fact, they could get triangles of silver, so little nanoprisms, whose the length of the side of these nanoprisms depended on the color of the light that was shining in. And I was so fascinated by this process, right? Using light and the color of the light as a chemical, right? How beautiful is that? You can essentially add photons of a specific wavelength to your reaction bio and actually get materials of different sizes. And so I wanted to understand how this works. And in fact, if you look carefully, this is a plasmon resonance of silver nanoparticles. They start with little spheres, and then they shine the laser, and by growing these spheres, they essentially make bigger and bigger particles. The plasmon resonance shifts towards longer wavelength. However, if you, for example, look at the 470 nanometer excitation, and you look at the particles that you make out of it, you get this kind of fact that essentially everything grows past that excitation, and once that excitation, once the plasma resonance doesn't resonate, essentially the reaction stops. And so I thought, this must be heating. Because in fact, in these solutions, they were adding a reactor that is ascorbic acid that is well known in colloidal chemistry. It only works as a reducing agent, which is needed to grow metals if you heat up above 60 degrees. And so I thought, well, it must be heating, right? This is all just heating up the solution of nanoparticles and activating chemistry like that. So it's nothing special. It's not like any non-thermal process. This is purely thermal. So that's a hypothesis. All plasmon-driven nanoparticle synthesis are due to photothermal activation of the reducing agents. That's the hypothesis that started my independent group leader career with 7 or 8 years ago. And before I continue, I want to quote Niels Bohr, who said, "An expert is a person who has made all the mistakes that can be made." There you go. I'm proud to say that I'm an expert in plasmonic chemistry. Okay, so first question is, okay, you think that you shine light on suspension of nanoparticles, they grow, and you say, well, this must be temperature. Why don't you put a thermometer inside the solution and verify this is temperature? Yeah, no, that's simple. In fact, it's very hard to measure the temperature of a solution as you shine a little into it, particularly of a solution that contains nanoparticles that are extremely efficient at scattering out the particles. And there is many reasons for it. First of all, light is not absorbed and scattered equally on both ends of the event. There is large temperature gradients that can generate activated. Large temperature gradients actually lead to convection and different paths of conduction of heat. Thermocouples that are typically used to measure temperature are photosensitive. The rate of chemical reactions that you measure is not linear dependent on temperature. You make a small mistake in temperature with huge change in the reaction rate. So it's not very easy to do that. It's not as simple as putting a thermocouple inside. So what we said is, okay, we need to study a model system that we know exactly how it behaves at different temperatures, and then we measure it under light irradiation and compare it to experiments in a very controlled way. So that's what we set out